Hey folks, Professor Gray here. Ready to talk about the fundamentals of probability for probability and statistics, or introduction to statistics. Well, what is probability anyway? Well, definition is how often something occurs or is expected to occur. And other than the fact that the name of the course includes it, why do we study probability? Well, probability gives us more information about the data that we're interested in. It's also easily accessible. Most people of a certain age are familiar with the basics of probability. When you listen to the weather report and hear that there's an 80% chance of rain, most people, even those who have not had statistics courses, understand what that means, or at least understand that that's a good chance. And another reason is the rare event rule and its use in inferential statistics. Here is the rare event rule for inferential statistics, defined. If under a given assumption the probability of an observed event is extremely small, then the assumption is probably not correct. The event itself is called statistically significant because it's just too unlikely to happen by chance, just out of the blue. Statisticians and we will use this rule to infer things about populations and to make generalizations and decisions about populations. That's inferential statistics. Imagine a scenario. You make the assumption that most dogs have dark fur. So you go to a dog park and you sit on a bench and you watch people come in with their dogs to walk them and play frisbee and whatnot. And you count the number of dogs that have dark fur and light fur. And you find that the number of dogs that have light colored fur far outnumbers the dogs with dark fur. Well, your assumption was that most dogs have dark fur. But if what you were seeing doesn't back that up, then your assumption is probably not right. That's kind of what's going on in the rare event rule for inferential statistics. You have an assumption, but then you see the probability of something you observed is very small. It's a rare event. Then there's probably something wrong with your assumption. If indeed most dogs have dark fur, then you should not see so many that have white fur or light colored fur. That would be a rare event. Those of you who are familiar with something called proof by contradiction, this may sound familiar. It is basically the statistical analog of that concept. Well, here are some more terms that have to do with probability. One of them is an event. An event is any collection of results or outcomes of a procedure. A procedure is something that is done or something that you observe. The event is a result. A simple event cannot be further broken down into simpler components. And the sample space is the set of all possible simple events of a procedure. Let's do a few examples. For example, let's find the sample space of a flip of a coin. If you flip a coin, the total possibilities or possible outcomes is heads or tails. Number two, let's find the sample space of two flips of a coin. Well, if you flip a coin twice, you can get heads and heads. You may get heads and then tails. You may get tails and tails, or you may get tails and then heads. Those are all the different possibilities. If you flip a coin twice, I guarantee you will get one of those four. Number three, sample space of a six-sided die. If you have more than one, they're called dice, D-I-C-E. If you have one of them, they're a die. You can get the numbers 1, 2, 3, 4, 5, or 6 if you roll one six-sided die. And number 4, the sample space of 3 births. Let's assume boy or girl. You can get boy, boy, boy in 3 births. Boy, boy, girl. Boy, girl, boy. Or boy, girl, girl. You can also get girl, girl, girl. Girl, girl, boy. Girl, boy, girl. Or girl, boy, boy. Those are the possibilities. Now, in number 2 and number 4, those are events, but they are not simple events. They can be broken down into smaller components. The answers for number 1 and 3 cannot be broken down any further. They are simple events. All of these are sample spaces for different scenarios. A tree diagram can also be used to help find a sample space or all the possible outcomes. Now, let's say you're at a party, and at this wonderful math party, you're going to play a math game. And in this game, you flip a coin, and then you spin a spinner with red, green, or blue, and then you flip another coin. Well, how can you tell how many possible outcomes there are? Well, let's make a tree diagram and see. To make a tree diagram, first start with a common point, and then I make lines to my first outcome. First thing you do in this game is flip a coin, so you can get either heads or tails. Then after you flip the coin, you spin a spinner and you can get either red, blue, or green. After you've spun the spinner, you flip another coin, so then you get heads or tails after that. And now I have a tree diagram. Every possible outcome for this game is represented by something on this tree. Heads, blue, tails is up there. Heads, green, heads. Tails, blue, heads. Tails, green, heads. All of them are represented. How can I find the total number of outcomes there are? Well, I could just count the number of leaves here on the end. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 outcomes possible. Maybe the object of the game is to get tails, red, heads, and if you do, you win. Either way, that's a tree diagram. For finding probabilities, it's important that we know how to find the number of events in a sample space. Now, this can be done with the fundamental counting principle, abbreviated FCP, permutations and combinations. In these notes, we will focus on the fundamental counting principle. All right, the fundamental counting principle is used to count things. For example, let's say you're going to camp or you're going on vacation for a week and you have 3 shirts and 2 pairs of pants. Well, how many outfits can you make if you take that in your luggage? The fundamental counting principle will help us find out. Here's how to find out using the fundamental counting principle. Some people call it the slot method because I'm going to draw slots. 1 for shirts and 1 for pants. All right, I have 3 shirts and I have 2 pants. Multiply those together. 2 times 3 is 6. So you have 6 outfits. And that's the answer. All right, question number 6. An internet password consists of 5 capital letters. How many passwords can be formed if each letter can be used only once? Well, I have 5 capital letters, so I'd have 5 slots to fill letters in. How many letters are available for the first slot? That would be 26. 26 is in the alphabet. Well, if I use a letter for the first slot, I can't use it for the other slots. So now I've got 25 left to choose from for the next slot. If I use a letter for the first slot and another letter for the second slot, I can't pick those letters again because the question says each letter can only be used once. So now I've got 24 to choose from. The next one I'll have 23 and the next I'll have 22. Multiply those together. I'm going to use the calculator for that. So I multiply all of those together and I get my answer. So there are 7,893,600 passwords available. Now that's why we haven't run out of passwords yet. I can increase the number of passwords if I include capital letters and lowercase letters, if I include numbers, if I include symbols, if I allow you to repeat numbers or letters or symbols, that number will increase astronomically. Yet the most common password, I think, is password. But don't limit yourself, there's a lot more out there. Number 7, how many ways can you put 6 books on a shelf? So let's say I've got a shelf and I've got 6 spots on this shelf for books. Well, for the first slot, I have 6 books that I could put on that shelf. Put a book out of the pile and put it on the shelf. Now I've only got 5 left to put on the second spot. If I take a book and put it on that spot, now I've only got 4 left. Then 3, then 2, then 1. I multiply those together according to the fundamental counting principle. And I get 720. 720 different ways that I can put those books on the shelf. Now it may just be that I like one of those ways, alphabetical order perhaps, but there are 719 other ways that I could do so. That's the fundamental counting principle. Now number 7, 6 times 5 times 4 times 3 times 2 times 1, that could have been written as 6 with an exclamation mark. That's 6 factorial. Factorial symbol denotes the product of decreasing positive whole numbers. For example, 4 factorial would be 4 times 3 times 2 times 1, which is 24. And by special definition, 0 factorial is 1. How do you put 0 things in 0 slots? One way. You don't do anything. Well, let's have a little bit of fun with factorials before we move on. If I go to my calculator and I find a 1-digit number like 9 and find 9 factorial, I get a really big number, 362,880. If I find a 2-digit number like say 12 factorial, I get an even bigger number. If I try an even larger number than that, let's say 37 factorial, I get 1.376, some other numbers, times 10 to the 43rd power. And if I try a three-digit number, let's say 102 factorial, that number is so large that the calculator cannot show it. It causes an overflow error. So the calculator taps out and can't show you that number. It's so large. Factorials get very big very quickly. But they help us calculate the size of a sample space. Well, once we know the total number of simple events, we can calculate probability. Where P denotes probability and A denotes a specific event, the probability of that event is found by the number of occurrences of the event divided by the total number of simple events. In other words, total number of ways it happens divided by the total number of possibilities. Let's do a few examples. Number 8. We'll find the probability of rolling a 2 with one roll of a six-sided die. So for number 8, I write my notation first, and I write it like this: P of x equaling 2 equals. Now this is saying probability of, parentheses, x being 2, or x is 2, is. So that's the notation that we use to communicate that this is a probability that x is 2 or x will be 2. Well, how many sides have a 2 on them on a six-sided die? That would be 1. So I have one side with a 6, or excuse me, one side with a 2, and there are 6 sides total. So 1/6 would be my answer as a fraction, or if I write that as a decimal, I can do that. We usually round those to either 3 or 4 places. 0.1667. And I use the approximately equals to symbols to show that I have rounded that. Number 9. What's the probability of rolling a 12-sided die and getting a number greater than 3? Alright, notation first. Probability that x is greater than 3. How many sides are greater than 3 on a 12-sided in this case? Notice the directions, 12-sided die. 4, 5, 6, 7, 8, 9, 10, 11, 12. So 9 sides out of 12 are greater than 3. As a decimal, that's going to be 0.75. And I actually don't need the squiggly marks for those, or the approximately equal to for those. I'll use the strictly equal to, which is more accurate. Number 10. It's the probability of picking an ace out of a standard deck of cards. Alright, so probability of an ace, I can write that like this, is, well, how many aces are in a standard deck? That would be 4. out of total number of cards, 52. If I reduce that, I get 1/13, or as a decimal, 0.0769. is my answer. That's about an 8% chance. Generally, we leave probabilities in this course in decimal form. We don't convert to percentages. Number 11, if 5 balls are placed in a bag, what's the probability of picking a red ball if 2 of them are red? All right, so probability of a red would be, well, how many are red? 2 out of 5, which is 0.4, 40%. That's how you find fundamental or basic probability. Let's talk about the different types of probability for a moment. There's classical probability and there's relative frequency probability. If each event has an equal chance of occurring and you calculate the probability without actually doing anything, that's classical probability. If you record data from a procedure, then that's relative frequency probability, and that's an approximation of the true probability. So, if I give you a coin and tell you to flip the coin 10 times and write down how many heads you got, find the probability of getting heads, that would be relative frequency probability because you actually did a procedure and recorded the results. If I were to ask you, well, what's the probability of getting heads on a flip of a coin? Well, you would say 1/2 or 1/2, 0.5. Then you found the classical probability. You didn't actually do a procedure, you just found what the probability should be. Now, the law of large numbers links the two. As a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. That means the number of trials is more accurate. A larger number of trials is more accurate. If I give you a quarter and I tell you to flip that coin 10 times, you might get 5 heads, you might not. If you flip it 100 times, you might get 50 heads, you might not, but it'll be closer, more likely than not. If you flip a coin 1,000,000 times or 1,000,000,000 times, the numbers of heads will get closer and closer to the classical probability 50% of the time. Now, this is why casinos make so much money. They pick games in which the odds are in the favor of the house, the casino. So the longer the gamblers play, the more likely the house will win and take in money because the odds are in its favor. As the numbers get larger and larger and number of trials increase, what actually happens will match the odds of the game. What actually happens will match the odds of the game, and the house will win more money than the gambler. This is also how the lottery is able to give away millions of dollars and still make millions more. The odds are in the favor of the lottery, so even though they're giving away quite a bit of money, in the long run, law of large numbers, the lottery makes more money than it gives up. Next, we'll talk about some probability rules. We express probabilities in this course as a fraction, simplified, or decimal number, rounded correctly. For any event A, the probability of that event is between 0 and 1, or 0% and 100%. If the probability is 0, then A is impossible. If the probability is 1, then it is certain to happen. Complementary events consist of all outcomes in which an event does not occur. We denote it by putting a bar over top of the event. Well, if there's an 80% chance of rain, what's the probability it will not rain? Or the complement of it raining? Well, it would be 20%. How do you know that? Because you took 100% and subtracted 80%. That's the complement rule. Probability of something happening and something not happening will always add up to 100%. As long as the events are mutually exclusive. So for number 12, what's the probability of not rolling a 2 with one roll of a 6-sided die? Well, earlier in number 8, we found the probability of rolling a 6-sided die and getting a 2. So for number 12, we want the probability of the complement. I put a bar over x equals 2 to show I'm finding the complement. So that's 1 minus the probability of x equaling 2, which is 1 minus 1/6 which would be 5/6, or as a decimal, to 4 places, 0.8333. Number 13. What's the probability of rolling a 12-sided die and not getting a number greater than 3? Well, this is the complement of number 9. Probability that x is greater than 3 complement is going to be 1 minus 0.75, which is 0.25. Number 14. Find the probability of not picking an ace out of a standard deck of cards. This is the probability of an ace complement. We found in number 10 the probability of getting an ace was about 0.0769, so 1 minus that. That's going to be about 0.9231. That's approximate. Number 15. 5 balls are in a bag. What's the probability of not picking a red ball if 2 of them are red? This is number 11's complement. So this is the probability of red complement. 1 minus 0.4 is 0.6. That's how to use the complement rule. In the next video, we'll talk about disjoint events and other probability rules.